carrying on with our look at locus and complex numbers. So yesterday we looked at different shapes, so circles and lines and things like that. Today we're going to look at functions. So you've got a function, but it's involving complex numbers now. So omega would be some function of z. Find the locus of w or z, depending, and they will usually give us some condition that we have to apply. The idea being, to solve these problems, we try and make whatever it is they've given us the condition for, we make that the subject of this formula, because that's the thing we know about. So once we've got an expression for that, we can deal with it. Some common ideas. One of the conditions I'll say a lot is that one of the complex numbers is purely real. And that then would lead me to conclude that means the imaginary part must equal 0, or I might play with the arguments and say, well, the argument must either be 0 or pi if it's purely real. And the flip side to that is they might tell me it's purely imaginary. In that case I could say, well, the real part must be 0, or the argument would be either plus or minus pi on 2. Then you've got this interesting one that comes up a bit. You see this thing where it says argument, and then there's a fraction, and both the numerator and the denominator are linear functions. You see that situation, and it equals some value. That turns out to be an arc of a circle. Now, what type of arc? If that angle turns out to be greater than pi on 2, then I know it's a minor arc. If it's less than pi on 2, it turns out to be a major arc, and then if it's actually equal to pi on 2, it turns out to be a semicircle. Okay, let's try a few. So here's the function. W is equal to z plus 2 on 2. The modulus of z is equal to 4. Now what's happening here is we're saying we're going to get every complex number whose modulus is 4 and substitute it into this function. What does the answer look like? What does that picture look like? What we're doing here is drawing a function, but it's in 4 dimensions, and this is what makes it difficult to visualize. See, when we're dealing with real numbers, we have an x-axis and a y-axis, and we substitute the x in and we get a y value, and we can plot that point. But now we're dealing with complex numbers, and each of those has 2 parts. So we're going to substitute in a real part and an imaginary part. There's 2 numbers. And it will output an answer which has a real part and an imaginary part, and that's 4 numbers. That's 4 pieces of information. How do you plot that? Well, you need 4 dimensions to do it. Again, this is something we can't visualize in our heads because we live in a 3-dimensional world. So what we do then is imagine 2 different Argand diagrams, one for the input and one for the output. And so on the input, we'd be getting everything that is on that circle with radius 4. And we're saying, well, what would the picture end up being on the other Argand diagram? What would that look like? Let's see what it does. Well, the idea I said was make whatever the condition is the subject. So let's rearrange this and make it the subject. Let's make z the subject. ZW is z plus 2. Play around with that. And there we have it. Z is 2 over w plus 1. I can now work out a locus for w because I know is equal to 4. So there's my answer. 2 on w minus 1 is equal to 4. Now, I don't immediately recognize what that is. I need to play around with it to get into something I recognize. So alright, well, modulus of 2 I know is 2. Then on the bottom, just modulus of w minus 1. Rearranging that, I've now got something I recognise. It's also a circle. Its centre would be at the point 1, its radius is a half. And so there's our locus. Centre 1, 0, radius a half. I'll also give the equation. I mean, they haven't said how they want the answer, so I've just given it a couple of ways. I've described it. I've also given it its equation. Okay, this one. So w, z plus 1 on z minus 1, and this time they put the condition on the output. W is going to be purely real. Well, W is already the subject, so I don't need to go any further there. I've got what I need. But purely real, there's the trigger. That tells me the imaginary part is equal to 0. So I need to work out what the imaginary part is. So I break it up into real and imaginary. So I get x plus 1 plus iy over x minus 1 plus iy. Need to realise the denominator for that, so multiply by the conjugate, and boom, there it is, expanded out. Well, I'm only interested in the imaginary part. The nice thing about this is I only have to look at the numerator because the denominator is purely real. What's going to make it imaginary is the x plus 1y I and the x minus 1y I. That's got to equal 0, and because it's 0, I don't need to worry about the denominator, because if a fraction's equal to 0, it's got to be the top of the fraction that's equal to 0. So essentially I just have to solve this. That'll tell me an answer. So let's play around with it, and it just simply is y equals 0. Y equals 0, the x-axis, or the real axis in our other diagram. So there is, but this is where we have to be careful. You notice I've excluded the 0.10. Why have I done that? Because you've always got to go back to what the original question asked. See, I changed it into this so I could find a solution. Got me the solution y equals 0. But the original question was w is equal to z plus 1 on z minus 1. Well, we're saying locus of z. We're saying what can we input into this function? Well, the bottom of the fraction can't equal 0. So I know I can't substitute in the number 1, or 1 plus 0i if you like. So to exclude that point, 1, 0. There's another way I could do it, is playing with the arguments. Some people find this a lot quicker. Now, if w is purely real, then I know the argument has to be 0 or it has to be pi. So we're saying the argument of z plus 1 on z minus 1 is equal to 0 or pi. Think about what this says. Argument of z plus 1 over z minus 1. If I was to play with the rules, I get argument of z plus 1 minus the argument of z minus 1 is equal to 0 or pi. Well, what was argument? That's the direction of the vector. So we're saying the difference in the direction of the vector is either 0 or it's pi. We've got to be talking about the same line, because there's no difference in the arguments. They've got the same direction. Or pi, they're going in opposite directions. Let's draw a picture to try and see what that is. Okay, so we're saying we've got the point z. We're going to join it up to -1, and then the other one join it up to +1. So this is the illustration where they're in the same direction. So if I was to put z over here, any vector coming out from 1 is going in that direction. Any vector coming out from -1 would go that. They're going in the same direction. So the difference in their arguments is 0. If I was to put it on the other side, same deal. Coming from -1 it's going that way, coming from +1 it's going that way. They're going in the same direction. If I was to put it in the middle, so our next picture here, that would now get in between. Because if I was to put it, say, here in the middle, the vector from -1 is going that way, and the vector from +1 is going that way. So they're going in opposite directions. So that would be the one where their difference is pi. So when we see this situation where the argument is either 0 or pi, we know we're talking about a straight line that goes through these 2 points. But not including those 2 points. Remember, when we're drawing rays, because that's what a vector is in complex number, it's a ray, we don't include the starting point. Well, hang on, that contradicts the other one. It only excluded one of the points. So this solution excludes both. But again, you go back to the original one and just make sure. And so if we go back to the original question that was asked, if I substitute in +1, sure enough we can't get an answer because you get 0 on the bottom of the fraction. But if I substitute in -1, I can get an answer because it's simply 0. Because on the top of the fraction we get 0, but on the bottom of the fraction you get -2, and that's fine. 0 over -2 is 0. It does work. So if we use these methods, either way, you still got to have a look and just test what may or may not be exclusion points. I mean, the second one brought out the possibilities quite nicely. The first one, we had to sort of go searching for it ourselves. Answer whatever the original question was. That is what you make sure of. You might transform the question into something else to help you solve the problem, but always go back to what was the original question. Make sure you're answering that. All right, let's do this one then. Argument of z on z minus 4 is pi on 6. So this is the one where we saw argument, and I've got a linear function on the top, which is z, and on the bottom of the fraction is another linear function, z minus 4, equal to some number. Conveniently it's in radians for me. Pi on 6. I know this is going to be the arc of a circle. Where does it come from? Again, same as I just did with that last one. Argument of z minus the argument of z minus 4. The difference in the arguments is pi on 6. So now we're not talking about a straight line, because it's not 0 or pi. Now we're talking about this arc of a circle. Okay, well, let's draw a picture and try and visualize what's happening. I got an arc of a circle. Question is trying to work out where it is. And this is where geometry is far superior. Argument of z minus the argument of z minus 4 is pi on 6. Again, some random point z, if I join it up to 0, but also join it up to 4, then the angle between the two, or the difference of the arguments, will be pi on 6. And you'll notice I've put it underneath the x-axis, and that's because I know what the final answer is going to be. Z turns out to be below the x-axis on this one. Now, how did I know that? It's like this. The argument of z must be bigger than the argument of z minus 4. You see, because when we take it away, end up with a positive number. So I know that must be true. The reality is when I do these, I always assume they're above and then see if it works. So if it was above, then it's a lot easier to see which one has the bigger argument. In this case, the bigger argument is z minus 4. Well, that's not what we want. Therefore, it must be below, not above. Because when you go below, you're now playing with negative numbers. That's still a bigger angle, but it's a negative number. You've got a negative small number minus negative big number. Minus minus is a plus, becomes positive. Okay? So as I say, I'll always assume it's above, just play with it and have a look at it and go, yep, no, works or doesn't work, and then I can work out whether I'm above or whether I'm below. Now, because I know this is going to be an arc of a circle, then the line joining 0 and 4 must be a chord. The next thing I notice, it's all about circle geometry here. The perpendicular from the centre bisects the chord. So if I want to find the centre of the circle, I know that the line from the centre will go through the midpoint of the chord. That's why I've now labelled in 2. It's the midpoint of the chord. The perpendicular from the centre bisects the chord. So if I draw a line perpendicular to that, then the centre must lie on this line. Now the centre must be below the x-axis because I'm dealing with a major arc. I'm dealing with a major arc because pi on 6 is less than pi on 2. If you think about drawing a circle, where's the centre? Well, if it's a major arc, it must be on this side of the chord. If it was a minor arc, then I know the centre would have to be on the other side. So I know the x-coordinates because I've got a vertical line. Now I've got to try and find the y-coordinate of the centre. Okay. Well, there's the radius. I'm going to need that as well. I don't know what that is yet, but let's just work it out. That's going to be 30 degrees. Now, how do I know that? Another circle geometry theorem. The angle at the centre is always twice the angle at the circumference standing on the same chord. This is 30 degrees at the circumference, which means this whole angle at the centre of the circle must be 60 degrees. But in this right angle triangle, then half of that becomes 30 degrees. I've got enough information now, I think, to work out what I need. Y over 2 will be the tan of 60 degrees in that right angle triangle. So y is 2 root 3, but hang on a sec, I'm below the axis, so actually that y coordinate will be minus 2 root 3. So I have the centre of this circle. Now, radius, I can now do Pythagoras, and I get that the radius is 4. Let's now describe the locus. Locus is the major arc of the circle, x minus 2 squared plus y plus 2 root 3 squared equals 16, formed by the chord joining 0, 0 and 4, 0, but not including these points. Not including? Well, if I was to sub 0, 0 in, then I'd get the argument of 0, because it'd be 0 on the top. Well, 0 does not have an argument, so that doesn't work. If I substitute in 4, 0, then the bottom of the fraction becomes 0, and I can't have that either. So both of these points are excluded in this case. Another way you could say that, still the same circle of course, but you could say, but it's where y is less than 0. So you might tell you what the range of it is. But you need to mention some restriction about that. 1f.